My name is Rachel House, and welcome to my talk, Boost Your Data Literacy with 2 Key Concepts. First, I'll go ahead and introduce myself. I am currently a Senior Developer Advocate at Great Expectations, a data quality company. Great Expectations is the creator and maintainer of the popular Python open source data quality testing library of the same name. And we also offer a fully managed SaaS platform for data quality monitoring and management, GxCloud. So go check us out. Though I'm now in a developer relations and education role, most of my 17-year career has been spent as an engineer in a variety of data and data-adjacent fields. I'm a technical learning and communication enthusiast, and I really dig creating talks that break complex concepts down into relatable pieces. So now that you know a little more about me, let's go ahead and dive into data literacy. When dissecting any topic, I like to begin with the what and the why. What are we talking about? Why is it important? And critically, why do you care? So the why starts with DBT's State of Analytics Engineering report from earlier this year. And when I read the report, what really stuck with me was the finding that data literacy continues to be such a widespread challenge for data professionals and their non-technical colleagues alike. You know, data is a part of just about all of our work and lives these days, but yet professionals still struggle to communicate and collaborate effectively when it comes to data. Data literacy is a pretty broad scope of knowledge and skills. And to define it in a modern business setting, really, to be data literate means that you are versed in the competencies of working with data. Now, working with data is still a wide and expanding horizon of disciplines, all of which have their own unique depth of knowledge and skills that comprise competency. So even if you're a data professional, there's both a breadth and a depth of competency across disciplines that you don't engage with on a daily basis. And if you're not a data professional, the task of becoming data literate can be pretty daunting in an organization that's running a modern data stack. The notion of becoming data literate can seem pretty monolithic. You know, where do you start? Do you learn pandas so that you can pull data into a data frame? Do you verse yourself on the benefits of common table expressions? Or do you develop really, really rabid opinions about pie charts? Working with data as a professional absolutely requires concrete skills and knowledge. However, the average data stakeholder isn't in the weeds of these skills every day. You know, often their time and effort is spent learning a tiny, discrete subset of the landscape that's then forgotten once the project or immediate need or crisis is over. This is not an enduring or efficient approach to data literacy. So what can we do about it? What we can do instead is synthesize the knowledge that's typically picked up piecemeal into broader foundational concepts that are more easily grasped, remembered, and most importantly, applied by stakeholders. In short, we need to lay a foundation for data literacy. We and our stakeholders can benefit from practical concepts and mental models that foster an informed mindset for how we reason about working with data. And even if the specifics of our data competencies vary as we get deeper into our own data and business domains, we can still relate and collaborate across disciplines using the same base concepts of what data is, how it works, and how we can achieve outcomes with it. So today, we're going to enjoy a data literacy double feature and explore 2 of the favorite concepts I've applied in my own career when thinking about and educating about data: the data supply chain and ML in a nutshell. OK, we've covered the what. We've covered the why. Now, I want to talk about you. Lack of data literacy. It's an issue that affects us all, data professionals and our non-technical colleagues alike. Here are my goals for the talk today and how it benefits you. If you're a data stakeholder, this talk will equip you with data fundamentals that enhance your ability to reason about data. in the context of building products and achieving outcomes with that data. It'll help level the conversational field when it comes to talking to your data teams about your data needs. If you're a data professional, this talk will provide packaged metaphors and concepts that can be shared with your data stakeholders. You know, data literacy is often talked about as a top-down endeavor in a lot of organizations. But in reality, data understanding and data reasoning is heavily fostered by peer-to-peer interactions. Colleagues need to help each other out. So, to that end, experienced data professionals can still benefit from ideas that they kind of know intuitively, being expressed in a digestible way that can be shared with non-technical stakeholders. And if you are data curious or an aspiring data professional, this talk will help jumpstart your understanding of working with data and will provide a practical base to grow your skills. All right, so with the stage set, let's move on to Act 1, the data supply chain. A key part of working with data is understanding its journey through the world. Raw data is a resource. However, raw data in of itself is not inherently useful or profitable. It needs to be transformed and enriched so that humans and machines can extract patterns, trends, and insights. To that end, information is the end result or final product of raw data. The reality is that data is continually and progressively cleaned, transformed, transferred, shared, linked, aggregated, and reshaped as it progresses from its original state to one that's more immediately insightful and applicable for us humans, and now for machines. So it's this set of actions, these changes and refinements, that constitute the data supply chain. Data is a product. It's long been an internal product for organizations, used in operations and business analysis, but increasingly it's also a product sold to external customers. And when we think about treating data as a product, we can draw analogies from how tangible goods make their way from raw materials to consumable products. Supply chains are built upon a series of key steps: collection of raw materials, transformation of materials, assembly, shipping, storage, and just as these steps require engineering, management, and quality control for their tangible products, so do they for data products. At every stage of the supply chain, tangible or digital, we have producers and consumers, inputs and outputs. And we need to be able to validate the quality of our product at each stage and its fitness for purpose at each stage. In real-world organizations, our supply chains manifest as infrastructure containing data stores and data pipelines. In data stores, we house data at rest. When in a store, data will exist in one incarnation of the many states it manifests as it undertakes its journey through the supply chain. Data pipelines move data from one store to another. And usually, but not always, they process and transform the data as part of that transit. So what we see here, the journey of data from one store to another via a pipeline, that's really just a single step in the data supply chain. Data's journey through the supply chain typically involves many iterations of storage pipeline storage. Just like when we transport physical materials through their intermediary stops and as part of their supply chains, from warehouse to processing facility to distributor to consumer. When it comes to the data supply chain, we have the notion of upstream and downstream. Upstream is toward the source, downstream is away from the source. And source here is relative. For our supply chain up on the screen, we may have multiple upstream sources relative to where we reside in the chain. Now, in a data supply chain, if changes are made to data upstream, they propagate downstream. A change in data definition or quality upstream continues to flow downstream and can impact subsequent users, consumers, and other pipelines that touch that data. This could be positive, like if a restaurant started sourcing more nutritious, higher quality produce for their meals and in-house catering. Or it could be negative, like introducing water contamination at a municipal water plant. This is why quality assurance, data quality assurance, is essential throughout this data supply chain, particularly where transformations occur. When your data product is only monitored for quality at the very end of the chain, right before consumption, it becomes difficult to impossible to diagnose and rectify the source of the quality issue. And further, we're almost never dealing with a single or just a simple series of pipelines to get from our source raw data to our end-use target data, whether that's for a query, a dashboard, machine learning model, some other data-driven goodness. Our modern-day data supply chains are these beautiful, complex messes of interconnectedness that involve many dependencies, transformation, linking, augmentation, storage, and delivery. Data is used at all stages of its life cycle and at interim points throughout the data supply chain. If one man's trash is another man's treasure, well, then one person's raw data is another person's final product. And as large and involved as a single organization's data supply chain might be, it's still only a microcosm of the much larger data supply chain that's running through our age of information. If your company's using third-party data, well, that data's already been through many steps in its own supply chain before it ever hits your stores. All right, now that we've looked at data's journey through the supply chain, I want to return to this notion of data as a product. We've looked at infrastructure. Now let's focus on what's getting delivered and how it's used. Data is really easy to think about, talk about, and treat as this abstract entity that's just there, magically fueling our applications, informing our businesses, and keeping the digital world just chugging along. Further, we've done a really excellent job over the past couple decades of hyping this notion that if you're a business and you use data, then you are going to promptly and radically revolutionize your operations and reap that sweet, sweet data-driven profit. A complicating factor in this is that we've adopted a single, all-encompassing term, data, for this product that varies wildly in format, definition, quality, and fitness for purpose. So, while it may seem appropriate to assume that if a data consumer needs data and we just give them the data, then that solves the problem. Well, the unsurprising outcome is that no, it usually doesn't. Data's utility as a product is different depending on who's using it and for what purpose. Different data disciplines and data personas have different data needs, and they also source their data from different points of the supply chain. If your mom's knitting you a wool scarf and asks you to bring her project materials, do you show up with a sheep? Nah. If your dad's baking a cake and needs some eggs, do you give him an omelet? Also no. Similarly, if you give a data scientist a PDF report with some summary sales figures, it's still data, but it's in the wrong format and wrong granularity for that data scientist to be able to train a model to predict, individual price points that you should set for your products. For data to be useful, it needs to be in the right format and contain the right contents. Just because there is data doesn't mean that it's automatically applicable or useful. Data scientists, data analysts, data stakeholders, they all source their data from the supply chain and are key consumers. However, each of them have different data needs. Data scientists typically need their data from early on in the supply chain. Their work requires data to be in its native format with no or minimal prior processing, and they really want as much data as possible. Data analysts tend to source their data from mid-chain, where it's gone through some assembly and transformation, but there's a degree of preparation required to glean insights from that data. And data stakeholders, such as business professionals and executives, they source their data from the end of the data supply chain. They need pre-packaged, consumable data that serves up the insights on a platter. In dissecting the data supply chain, we've explored how data is delivered, how it's delivered to its consumers, and we've also touched on a few key uses of data. Now, I'd like to zero in on a specific use of data, and that's machine learning, or ML. So welcome to the second half of our future, ML in a nutshell. There we go. All right. Machine learning can be grouped into three key categories: supervised learning, unsupervised learning, and reinforcement learning. In supervised learning, you program computers to learn from past experiences to generate predictions. In unsupervised learning, you program computers to surface patterns in data without the use of historical examples. And in reinforcement learning, you program computers to attain a complex goal or objective over many steps. We're going to focus on supervised learning, which still constitutes the majority of machine learning done today. You just saw that all of the categories of machine learning involve programming computers. Program a computer to. Machine learning is a programming paradigm. It's a new way of communicating your wishes to a computer. Previously, to program a computer to produce an output based on an input, you likely would have written a set of explicit imperative instructions on how to perform that mapping. But with machine learning, you provide a collection of example input-output pairs, and the computer figures out how to do that mapping. And generally, with supervised learning, you're dealing with two classes of activity: classification and regression. Classification is just like it sounds. You program a computer with examples to predict the class label or category of the input value. Simply put, you program a computer to label a thing. Is this a picture of a cat or not a cat? Is this a normal data point or is it an outlier? Regression is programming a computer to predict a continuous value or assign a number. Given a set of house characteristics, predict a sales price, or given today's environmental factors, predict tomorrow's temperature. Now, how do we program a computer with examples? Well, that's the essence of training a machine learning model. To train a model using supervised learning, the first thing you need is labeled data. Labeled data consists of input-output pairs that contain both the input and its desired output, or label. You need both the exam question and the answer key, so to speak. An example of labeled data might be an image file of a cat or dog, along with its class label: cat or not a cat, or potentially cat or dog if you're doing multi-class. It might be a sentence with the individual words and parts of speech, individual words and phrases labeled with their parts of speech. Or it could be a product review, along with the user rating given to that product. For supervised learning, what's key is that you need data that represents the problem that you're trying to model. And before training a model, you separate your data into a train set and a test set. One set of examples to train your model, and the other set to evaluate the performance of that trained model. Training the model consists of, first, selecting your learning algorithm, like a random forest, SVM, or neural net, and then setting the weights and biases, or parameters, used by that learning algorithm. You then use your training data set. You feed the training data inputs into your model and capture the output predictions. You next evaluate the training model predictions against your training data labels, namely your answer key, to determine how well your model's performing on your training set. From there, you iterate and tweak your parameters and weights and biases until you're happy with model performance. After you've completed training your model with the training set, you evaluate the model against a test set to calculate its performance. So from this flow of events, you can see how supervised learning uses data in the form of input-output pairs to create a model that's able to predict an output given an input. Training the model is the process of tuning the learning algorithm with its associated parameters such that the resulting model generates input-output mappings reflective of that training set. And when you're satisfied with your tested model performance, you've trained a model. OK, what happens next? How do we actually use that model outside of the confines of its test and evaluation environment? How do we generate business value with that model? In short, we connect it into the data supply chain. Deploying or operationalizing your model occurs when you connect a trained model to a source of incoming data and capture the resulting model predictions as output data. No model is an island, and models need to be integrated into your data supply chain in order to generate value. And when you run new, previously unseen data through your trained model, this is known as inference. Operationalized models will typically be deployed to use batch or streaming inference and connected such that their output predictions are housed in data stores that are accessible to downstream users and pipelines. Models become both producers and consumers of data in the data supply chain. Equipped with an understanding of how a model is trained and how it fits into the overall data supply chain, I'd like to return to the role of data in supervised machine learning. OK, so in supervised learning, the successful development and application of a model relies heavily on that data used for training. We saw that what's learned is gleaned entirely from those input-output pairs used for the train set. It's not magic. To develop a performant model requires data that's representative of the problem or task being modeled. To that end, one of the most expensive and time-consuming aspects of machine learning is often just gathering suitable training data. And further, with many of the learning algorithms today, deep learning in particular, not only do we need good data, but we need a ton of it. Much in the same way that typos, logical errors, and poor assumptions impact the performance of conventional software programs, problems with data quality cause subsequent problems in models trained with that data. Now, a popular way to express this effect is garbage in, garbage out, which is about as subtle and as helpful as saying, well, if you hit yourself in the head, it's going to hurt, so don't do it. Not very helpful. There's data quality problems that are overt and easily identified, like missing data or invalid values. Obvious garbage is increasingly straightforward to catch, thanks to data testing. The real data challenges in developing ML models are often more nuanced. The assessment of where on the scale from pristine to hot garbage data falls can be a complex question that requires both technical and business domain expertise and often requires collaboration across data disciplines. For instance, a data engineer might assess data quality on the basis of schema adherence, but a data scientist might define it based on data distribution. And an executive might care most about timeliness when it comes to data quality. We regrettably don't have time for a deep dive into data quality today. So first, check out Great Expectations. And two, I'm going to touch on arguably the most important data quality dimension for ML, and that's bias. Bias occurs when data is incomplete or inaccurate. Another way of thinking about it is when data is limited in some way. And those limitations cause the data to fail to represent what it's trying to capture accurately. Biased data is not representative of reality. And as we saw, when a model is trained on data, its understanding of reality is based solely on that data. Biased data encodes a biased worldview into a model. And this is really problematic when we're trying to, first, model real-world problems, and two, when model predictions increasingly have real-world outcomes and effects. However, this can be really easy to overlook, right? Because regardless of bias, a model is going to do what it does. It's going to map an input to an output. Models are not good at saying, I don't know. They won't reject a request to make a prediction because it's outside the scope of their cultural or emotional understanding. If an input is an outlier based on the training data, we can't trust the accuracy or validity of that prediction. And many of the problems we're seeing with ML and AI today are because we often treat all predictions blanketly based on biased data as valid, and because those predictions have real-world effects. Thus, when it comes to reasoning about working with data for ML, it's essential to understand the need for two things. First, you need to assess the suitability of your data for modeling. Is it actually representative of the problem that you're trying to solve? And two, you need to validate the quality of the data you're using for modeling. I'd now like to wrap up and highlight the key points from this talk. Data is a product that requires refining in order to be useful, applicable, and insightful. And the data supply chain is the infrastructure through which we deliver that data. Changes in data quality upstream affect downstream users. And data's utility as a product is different depending on who's using it and for what purpose. The needs of a data scientist differ from that of a data analyst, which differ from that of a data consumer. Machine learning is a programming paradigm in which data, not explicit instructions, are used to develop an input to an output mapping. ML models need to be integrated into the data supply chain in order to generate value. And the quality of data used to train a model impacts the performance and results of that model. Expertise across business and data domains is required to identify and address complex data quality issues like bias. Finally, let's zoom out to the overarching purpose of this talk. A strong foundation of data literacy fundamentals improves our ability to reason about working with data and contributes to successful outcomes of our data-powered endeavors. However, like so many things in life, developing data literacy is a journey, not a destination. It's not a problem we can conclusively solve for ourselves or for our peers. The way we work with data and what we can do with it, it's constantly evolving and changing, and so must our understanding. So, to that end, foster organizational understanding of the principles underlying what you're doing with data and why. Help directly equip your colleagues with the big ideas, concepts, and metaphors that enable them to relate to and ask questions about your day-to-day data work. And remain open to new ways of framing and explaining data concepts. And with that, thank you so much for your time and attention today. Thank you, DBT, for having me. It's been a pleasure being up here, sharing thoughts on data literacy, the data supply chain, and ML in a nutshell with you. And lastly, it's an honor to close out what's been a truly incredible Coalesce this year. So thank you.